Hello everyone. This is part 3 of topic 15 and 16. Part 2 got kind of cut off. I paused it and then I accidentally hit the wrong button, so I had to save it. So we're doing it in 3 parts here. But last time we showed what you see here, the development of the formula for the binomial expansion of 1 plus x to the nth. You can think of it in these terms, or if you want to think of the combinatorial coefficients. By that I mean the combinatorial coefficients you might remember, like NCR for combinations. And that's really what we're doing here. It's just MCK, let's say, is just the notation for M choose K. Okay? So it's just a different notation for combinations. So you don't have to worry about that too much. I mean, I'm going to use it as we progress through this example, but we're really just focusing on this general expansion that we had proven. So the example, it works for values of x that are absolute value of x less than 1. And that can be shown by the ratio test, but we're not going to take time to show that. But here it says find the first 4 terms of this expression. This is a binomial expression. And what you're going to have to do is find the value of m. And so it has to be of the form 1 plus x to a power. So if you want to take 1 step, 2 steps, taking 2 steps, 1 plus x to the 1/2 in the denominator, and then 1 plus x to the negative 1/2 when we exercise the negative exponent rule. So that just tells us the value of m is negative 1/2. And so basically all you have to do, if you look at this definition, you actually have the first 2 terms already, because you have 1 is always the first term, and then mx, and m in our case is negative 1/2. We just have to calculate these coefficients, which could be given by our combinatorial coefficients. So let me be formal here, and I'll say m choose 1 is m. So that implies that m choose, that m, or negative 1/2, that is, choose 1 is just negative 1/2. M choose 2, by definition, is m minus 1 over 2 factorial. So then for our example, negative 1/2 choose 2 would be m is negative 1/2 times negative 1/2 minus 1 is a quantity over 2 factorial. So basically you just have to grind down the arithmetic. So this can be negative 1/2 times minus 1/2 minus 1 is minus 3/2 over 2 factorial, which is 2. Okay, that gives us positive 3/4. And then I'll say times the reciprocal of the denominator 1/2 gives us 3/8. So that's basically our third coefficient, m minus 1 over 2 factorial in our general formula. And then we just need one more, m choose 3. And so formally m minus 1, m minus 2 over 3 factorial, giving us, for our case, negative 1/2 choose 3 is going to be minus 1/2 minus 1/2 minus 1 minus 1/2 minus 2 all over 3 factorial. So I'll take it slowly here. Minus 1/2 minus 1/2 minus 1 is minus 3/2. Minus 1/2 minus 2 would be minus 5/2. That's all over 3 factorial, which is 6. Okay, this gives us negative 15 over 8, and then times reciprocal of the denominator 1/6, and then 3 goes into 6 2 times, into negative 15, negative 5 times, so we get negative 5 over 16. Alright, so now we substitute into, if you want to rewrite the formula, in general, 1 plus x to the nth is 1 plus mx plus m minus 1 over 2 factorial x squared plus m minus 1 m minus 2 over 3 factorial x cubed. And that would continue, but we were just asked to write out the first 4 terms. So there they are. And then our value of m, here's our value of m minus 1. Here's our value of m, the negative 1/2. And then here's the value of m minus 1 over 2 factorial, that coefficient. And here's the value of our third coefficient. So therefore, we could say that 1 over the square root of 1 plus x is equal to 1 plus m, which is negative 1/2, times x, plus all of this is just the 3/8 times x squared, and then all of this coefficient is the negative 5/16 times x cubed. Okay, and that's all there is to it. Now, just for fun, let me just show you this. If you recall, way back when we first started, we showed how the graphs of e to the x, the graph of e to the x was approximated by these polynomials. And the more terms you picked up, the closer the approximation was. And then as an infinite series, it would represent the entire function. This gives us an approximation for this function, and I just want to illustrate with the calculator how close we are with just these first 4 terms. Let's say you can let x be, I don't know, 0.1, because I know, we made the note up here earlier that it converged for x being, absolute value of x being less than 1. So safely I'm going to pick 0.1. And then I'm going to calculate the exact value, would be 1 over the square root of 1 plus 0.1. So let me grab a calculator and do that, because that's our function. So 1 divided by the square root of 1.1, basically. Okay, so we get 0.953462589. That's what my calculator shows. Okay, and then the approximate value. That's plugging in a 0.1 for x into our polynomial. So 1 minus 1/2 times 0.1 plus 3/8 times 0.1 squared minus 5/16 times 0.1 cubed. Let's see, go into a calculator, let's see what we get there. So 1 minus 1/2 times 1 plus 3/8 times 1/2 times 0.1, I should say. So I made a mistake, let me do that again. 1 minus 1/2 times 0.1 plus 3/8 times 0.1 squared minus 5/16 times 0.1 cubed. And here's what we get for that. 0.9534375. So you can see that we're close to what the nearest tenth, 100,000th, 10,000th. We start to differ at the 100th, 10,000th. Start to differ at the 100,000th place. So just with those first four terms, it's a pretty decent approximation. And if you wanted to be more exact, just simply add on more terms. Okay. All right. So we got one more topic left to finish off the material for exam 4. So that's topic 17, and we'll see you when you're ready.